Okay, so let's start with our first question today. Let's start with topic 4 questions. Okay, the first question is about ethane reacts with bromine in the presence of ultraviolet radiation. Okay, so what is the equation for the reaction? Basically, they're trying to say, right? Okay, if we check out the alkane right here, which is C2H6, it is reacting with bromine. What are the products of this? The products is a halogenoalkane and a hydrogen halide, right? Because this is an substitution reaction. Whenever an alkane reacts with an halogen, a substitution reaction takes place, and this takes place in the presence of ultraviolet radiation. And in the substitution reaction, the halogen basically replaces any one of the atoms. In this case, it replaces a hydrogen atom and takes its place. So in this case, we can clearly see that one of the hydrogen has been displaced by bromine in option B, and the hydrogen which has gotten displaced, it reacts with another bromine molecule and produces HBr. Considering that bromine is a diatomic molecule. Okay, so one bromine basically attaches itself with the carbocation right here, while the other bromine basically reacts with the displaced hydrogen and produces the hydrogen halide. So our most logical answer would be option B. All right, both of you, did you understand?
Yes.
All right. The ultraviolet radiation is required for what type of bonding? Okay, in yesterday's class, I guess Mohideen was there, and Simra, I guess you also know this. Can you please tell me, in this case, we can clearly see that the bond to be broken is Br and Br, all right? Now, will it be homolytic fission or heterolytic fission? Obviously, it will be what? Homolytic fission. Why? Because both of them have the same electronegativity. All right, that means there is no electronegativity difference, right? So since there are no electronegativity difference, there is no the polarity of the bond is basically zero. And since both of them have identical electronegative values, so when they break down, each of the element will basically take equally the bonded share of electrons equally, producing radicals. All right. So in the type of bonding where both of the atoms or the elements take the shared pair of electrons from their bond, what is it called? It is basically homolytic fission. Whereas in heterolytic fission, the opposite happens. In the heterolytic fission, the higher electronegative element takes the shared pair of electrons during breaking. So in this case, since it's Br, the answer would be A. All alkanes have the same empirical formula, general formula, and structural formula. Okay. First of all, you need to understand this. The empirical formula is kind of not same for all the alkanes because the molecular formula is not same logic, right? So A and C are out of our options. This leaves the structural formula and general formula. Now, the structural formula basically depends on the molecular formula. All right. So if and since the molecular formula is not same for all the alkanes within a homologous series, then that is not also same for all the alkanes. This leaves us as the general formula as the only answer, because using the general formula, we can identify or interpret the molecular formula of each and every alkane within its homologous series. All right. And obviously we know that it is for alkane, it is CnH2n plus 2. Both of you guys, did you understand this? Simra, you're not responding.
Yes.
All right. Moving on, a single molecule of the decane, you can see that C10H22 is cracked. Which of these mixtures could not be formed? They say. Okay, so we have a decane right here and could not be formed. Uh, I think I taught you that when you basically crack long chain alkanes, what happens? alkenes plus shorter chain alkanes are produced. So if that's the case, then could not be produced, they say, right? Now, first of all, the alkane which is produced, it has to be shorter chain. Okay, so it has to be shorter chain basically, which is C10H22. There are 10 carbons on it. Now, B B might be produced and C might be produced because check this out. What did I say? That shorter chain alkenes and alkenes, these two things are produced, isn't it? So in this case, we can clearly see that ethene, propene, and I forgot to mention that what I mean by alkenes and alkenes is that at least two alkenes or at least two alkenes are produced. It doesn't matter basically, okay? At least two alkenes or at least two alkanes are produced. So if that's the case, that means B and C is possible considering according to my logic. So B will be cut, B is C could be formed. Now this leaves us A and D. Now, one thing's clear, that is that you have to remember that the alkene produced will not be greater. Always remember another thing, that the alkene produced will not have the higher chain than the alkane cracking produces two products. Okay, just remember one thing, which is that like I said, minimum two alkenes and two alkanes are produced in most scenarios, but there are some cases, very rare cases, where one alkene and one alkane is produced. All right. Now, if that's the case, then always remember that the alkene produced should not have a higher chain than the alkane. And here you can clearly see that both of them have the same chain, right? So it's not either, it's not greater. So that kind of basically, false in our logic. So this is possible, but if you check out in D, you can clearly see that the alkene's chain has a, it's longer, it is a longer chain than what, the alkane, right? So this is not possible according to our statement down here. So D is the correct answer, and it's the only mixture which cannot be formed. All right, did you understand how will you identify the combination? The combination is pretty simple. In most cases, two alkenes and two alkenes are produced. In some rare cases, one alkene and one alkene might be produced, but it's just that during that time, you just need to ensure the alkene produced should not have a higher, longer chain than the alkene. Did you understand?
Yes.
All right.
Yeah.
Now, how many structural isomers have the formula C3H6Cl2 has? Okay, fine. So if we check this out, basically, so you have, let's say, for instance, this one. Okay, so this is an example of one structural isomer. So uh, we have one three chloro or dichloro. All right. So if you check out another one, this might be another one, obviously. So the second one, and then if I check out another one, we have this and this third. So that's the first. This is the second. As the third. right? All right.
Also on the first carbon.
The first carbon.
Yeah, both CLs.
Yeah, sorry. Yes, makes sense. Yeah, the first carbon. That's the fourth one. So we have first, second, third, and the fourth carbon, which is in the fourth isomer, where you can see that in the first carbon, both chlorines are connected. So our answer will be C. Which pollutant cannot form when alkanes are burned in car engines, basically? All right. First of all, if we check out these options, obviously sulfur dioxide is produced and carbon monoxide is produced. All right. This leaves us carbon particulates and hydrogen chloride. Well, carbon particulates are basically dusts of carbon monoxide. So if carbon monoxides are produced, then particulates are also produced. That the only thing that will not be produced is hydrogen chloride. All right, because it's an acidic gas and it requires the presence of acid, but we don't have any acid inside. Uh, you know, in alkane flows basically. All right, we have sulfur though and carbon. The reason why sulfur dioxide and carbon monoxides are able to be produced. All right, so this is the answer. All right, a sample is provided, as you can clearly see. They said, and you need to solve this basically. So the first question is that calculate the molar mass of C. Okay, let us as first convert this into meter cube. Let us convert the volume first into meter cube. So you got 72.5 cm cube. If you want to basically convert this into meter cube, what do? You multiply it by 10 to the power 6. So if you do that, this will be your meter cube unit. Okay. Uh, you can just also write it in like, you just take the decimal point there. So it would be 7.25 meter cube, whatever you do it. All right, fine. Our volume unit arrangement is done. Now we tell you to find the molar mass, right? And we know that N here represents the number of moles. So for that, we need to find the number of moles. If I find the number of moles, we got PV by RT. All right, so you just plug in all the values and you get your N value. Okay, we have 100 kilopascal, right? So you just 100 times 1000 because you need to convert it into pascals. Then obviously this one 7.25 times 10 to the minus 5 divided by the mole gas constant, which is 8.31, and the temperature is what? It is about 358 Kelvin. So we don't have to convert it since it's already in Kelvin. So 358 Kelvin. Eventually, what you get is that uh, eventually you get about 2.437. Eventually you get about 2.4370 times 10 to the power minus 3 mole. So this is the mole amount of C. Now they told you to find the molar mass, right? So obviously you know the mass of that sample, right? So can't we use the formula mole is equal to mass by molar mass, right? So you just place 2.4370 times 10 to the power minus 3. Actually, I made a mistake. Sorry. Uh, 2.4370 times 10 to the power minus 3. And you know the mass 0.210, and they told you to find the molar mass. You just make the molar mass subject, and you can easily get the value. All right, which is about 86.172. 86.172 gram per mole. All right. I hope you guys understood this. Did you guys understand?
Yeah. Yeah.
Now, the organic liquid is the hydrocarbon. Give a possible name of the formula for C in your answer. All right. for this, we need to check out we need to check out the molecular mass down here. So we know that the molecular mass is about 86.172 gram per mole. Okay, let's just say it's 86 for our simplicity, for our calculations. All right, and they said it's a gas, right? So since it's a gas, then it must be an alkene. It must be an alkane. Sorry, it must be an alkene, because we know that among the hydrocarbons, refinery gases are the only ones which are in gaseous forms when we, you know, do it via fractionating. When we basically perform fractional distillation, and we know what are refinery gases made up of. It is made up of what? Propane, butane, alkane, propane, butane, basically alkane series. All right, now they said it's a liquid, right? Now since it's a liquid, then that means what? It basically means that it must have a longer chain. So I'm not assuming it to be having, you know, uh it should not be propane, ethane, butane or methane or of some sort, because since it's a liquid, that means it's not in gaseous form. So I'm not going to consider that in our mind. We know that after, from the sixth carbon chain, like if the carbon number basically exceeds 5, only then liquid starts happening, or liquid is found in gaseous form. All right, so remember this, that from C1 to C4, refinery gases of alkenes, refinery gases what? Alkenes in gaseous form are formed. From C5 to C8, most probably, or you can say C10, most liquid form of alkanes. Do remember this. That means we need to check with C5 and C6 and C7, C10. Okay, let's check with C5. If you find the molar, what is the pentane basically I'm talking about? So C5, 10, 12, right? And we have another one, which is let's try with C6H14. So try to find the molecular mass of this one and the molecular mass of this. Let's see which one matches with our provided value down here. My guess is C6H14 will match. Can you guys please check it out in your calculator? Fast. Find the molecular mass of both. I think you know how to find the molecular mass.
Pentane, 29.
What? Sorry.
For pentane, it's 29.
How come for pentane it's 29?
Sorry, wait. Sorry,
I
72.
Yeah, 72. And what is for C6H14? C
It's
14.
it's 86.
Yes, so that matches. So C6H14 is the correct answer. Did you guys understand how I did it?
Yeah. Yeah.
All right. All right, check this question. It's from January 21 to be exact. So they said here, which of these compounds have the same empirical and molecular formula? I believe it's very simple. All right. Uh, if you check out C, D, and A, all of them are even numbers, right? And they're basically what? Simplifiable. Say, for instance, for C4H10, if we simplify it by 2, it's simplified. Both of the numbers are simplifiable by 2. So obviously, we can give C2H5 as our empirical formula. And if we divide it by 5, then what comes? CH2. But you cannot divide C3H8 because one of them is an odd number and it is not divisible by 2. So obviously C3H8 will have this, since this is the empirical formula, The C3H8 is also going to be the molecular formula of that particular compound. So B is the correct answer. Now, which of these molecules is the most polar? Now, polar basically depends on the electronegativity difference, all right? And how do you identify the electronegativity difference? Well, you have to check out right here. You can see fluorine is the most consistent anion or the non-metal down here. And if we talk about the other options down here, we need to check out O, B, C, and H. Now we know H has the least value of electronegativity. So least and fluorine as the highest. So least and highest, obviously the electronegativity difference will be the highest in each F compared to the other three. So A will be the most polar bond. So we know, basically it means what? Higher electronegativity difference, more polarity. All right. A substance is labeled with the hazard symbol shown. What is the meaning of this symbol? Yesterday I showed to Mohideen. Can you please tell me what is the answer?
B.
B. Exactly. B is the correct answer. Corrosiveness. I don't think I need to explain it further because gloves must be worn is a measurement. It's not a risk or a hazard, and this symbol is a hazardous symbol. And do not store with flammable substance. In case of flammable substance, another thing is that this is not a hazard, it's a risk, or you can say not risk, it's a safety measurement. This is an hazard and this is an hazard basically, but obviously for oxidizing there is a flame sign, so obviously that's not the correct answer. B is the correct answer. Now, what is the IUPAC name of this alkane? All right. Now, for this to happen, you need to understand in a deeper way. So, at first you need to check out the longest chain hydrocarbon here. 2, 3, 4, 5, 6, 7, 8. This is the longest chain. So this is the longest chain of hydrocarbons. So obviously octane, considering 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons. So octane. So A and B is out of the equation. We need to come to C and D. Let us check out. They say 3, 4, 6. Is it possible? So you have 1, 2, 3. Okay, let's start from the this side basically. Let's start from this side. 1, 2, 3, 4, 5, 6. All right. 3, 4, 6. Tri, obviously. Ethyl. Uh, sorry, it's trimethyl. 2, 3 carbon. Makes sense. And if I take 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, one thing to remember, this was a little bit tricky, but the answer will be C. One thing you should remember all the time, that starting the counting, because if you don't start the counting in the right direction, then you might be confused. Uh, if you check out in the right side, you can see that there are two ethyl groups connected. Sorry, two methyl groups connected. All right, so always try to remember the side where the more ethyl groups are connected, or the side where the more methyl groups are connected. You're going to start from that side. So obviously we can see 1, 2, 3, 4. Like in 4 of the carbons we have seen that 2 methyl groups are attached. But if you check out in this way, 1, 2, 3, 4, only one methyl group is connected. So the greater priority is we are going to start from the right side. So 1, 2, 3, 4, 5, 6. So 3, 4, 6. Answer will be C. Did you guys understand?
Yeah.
Now, petrol, bioethanol, and hydrogen are fuels. All the three of these fuels basically burn what? They basically are overall carbon neutral. Obviously, they're not carbon neutral because they release greenhouse gases and provide have a huge impact on the ecological carbon footprint. So that's not correct. And overall sustainable, no, they're not sustainable because they might at one point of time they might just go. Biodegrade rapidly. No, they're non-biodegradable, so obviously BCD is not correct. But yes, all of these burn to produce greenhouse gases. Yes, it does. For example, when you burn hydrogen, bioethanol, or petrol, one way or another, carbon dioxide is released, which is a greenhouse gas. All right. Cyclopentane undergoes free radical substitution with bromine. Which of these is an overall reaction for this one? Okay, basically. Okay, first of all, a little while ago, I've showed you that what? A halogen and a hydrogen halide is produced. So obviously, we do not see any hydrogen halide being produced in A, B, C. So D will be our correct answer, considering hydrogen halide is produced. All right. Which statement is not correct about this reaction system? Only the initiation step involves the homolytic bond fission. Now, this might not be correct, all right, uh, because if you check out in the mechanism, we have what? We have initiation, and then we have initiation, and then we have what's it called? Propagation, right? We have what are the three steps? Initiation, propagation, and then there is another one which is termination.
Termination.
So not only initiation, in also in propagation also, homolytic bond fission might occur. All right, so this is not necessarily correct. Only some bromine is converted to free radicals in the initiation step. Yeah, this is correct because only some bromine is converted. Because then most of the bromine, I've told you that bromine gets or in other words, the bromine gets broken down in two steps: initiation, propagation. All right, and we know what happens in termination. All the free radicals which have been produced, they basically what join together to produce the final molecule. All right, so this is very important. And sometimes what the impurities are also present, like impurities as in some unwanted byproducts are also produced, but we will include them in the termination process, but we are not going to include them in the main reaction. All right, I think I've taken this class in with Simra, I guess. Now the next part is propagation forms more product than termination. Yes, it kind of does basically. Further substitution reactions are likely to occur. Yes, further substitution reactions might happen after the termination process. Why? I've told you, I've shown you this in that class, that after the main products are produced, if the main products are reactive or they have unpaired electrons, they might go through further substitution reactions and result to other products being produced. So the only thing which is not correct about free radical substitution is option A here, because homolytic bond fission can also happen in propagation. All right, so A is the answer. Which free radical is least likely to form in a propagation step in this reaction system? Okay, first of all, look, this is possible, and this is also possible, and this is also possible. We all know that, but we will never see hydrogen going through a propagation step because hydrogen will never have an unpaired electron. All right, okay, you do understand what I'm trying to say? Because why can I tell you? Because look, when Br and Br, and check out HBr. Okay, both of these will go, but there is a difference here you need to understand. For example, when you provide ultraviolet radiation, here homolytic fission does not take place. Here heterolytic fission takes place, and when heterolytic fission takes place, what happens? The bromine takes all the electrons from the shared pair of electrons. So in a sense, what does this dot represent? Unpaired electrons, right? Hydrogen is not going to have any unpaired electrons, all right? So it is least likely to form in propagation step, therefore. Did you understand?
Yes.
Which alkane could be formed in a termination step in this reaction system? All right, if you check out A, B, C, you have C5H10, so C5H9, alkane they say, right? So C5H9. So let's check out the number of alkanes. We have 1, 2, 3, 4, 5, 6, 7, 8. 7, 8, 9. So that's not correct. Uh, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's not correct either. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, there are 10 carbons here. All right, this is possible. And since it's a cycloalkane, so obviously D is out of the question. So 10, and yeah, this is possible. And then there is how many hydrogens? There are hydrogens about, you can see 9. We can see 10. So it is possible. We have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, C is the correct answer. This is the most possible alkene which could be produced in the termination step. All right, did you understand? In the
Yeah.
termination system, always remember that the alkane which could be formed, it is the alkane itself, this one. All right, because you will notice in the propagation step, what is going to happen? This will be produced. Okay, so if this gets produced in the termination step, all of these radicals will these radicals like C5H9 and C5H9, all these radicals in the termination step will react and eventually result in the production of C10, C5H10. Did you understand what I'm trying to say?
Yeah.
All right. This question is about the production of squalene, a liquid alkane which occurs naturally in human skin and is kind of used in cosmetics. Okay, nice. They said. Okay, so first of all, in order to solve this, you need to be a little bit uh, suggest two properties that make squalene very useful uh, in cosmetics. Okay, first of all, they have given you some idea suggesting two properties. Now, cosmetics, we use this in skin, right? So we can say it. What are the two most suitable properties which will allow us to use it in skin? Well, we can say it is a non-irritant, because if it was an irritant and when you would have applied in our skin would have turned red. So this is one property, sensible property that might happen. Give another one is colorless. If it was not, it was if it was non-colorless, then it would have been harmful as a cosmetic to be used in our skin. So it is colorless. These are the most two useful properties to be used in for that we tend to see in squalene, so that it can be used as a suitable cosmetics. Now, give the molecular formula of squalene. Well, all right. I'm giving you both Mohideen and Simra 2 minutes and tell me what is the molecular formula. It's a B compound. So can you please tell me? Count it out. So as it will have a practice as well. You guys will also have a practice. What do you get? Do you get 30? I believe I get 30 carbon.
C30H62.
Yes, this is the correct answer. Very smart. Okay, the next part is that squalene can be produced from an alkene present in shark liver oil by reaction with hydrogen gas in the presence of a suitable catalyst. Now, give the name of a suitable catalyst for the hydrogenation of squalene. Well, there are many ones. You can say palladium, platinum, or even nickel as well. So, any one of them. suits in this scenario. As long as it's a metal, it's a transition metal or a metal basically which is highly unreactive, we can provide it as a suitable catalyst. Now squalene used in the cosmetic products must contain no more than 0.2 ppm by mass of catalyst. So calculate the maximum permitted mass of catalyst in the product containing 50 gram of squalene basically. All right, so in order to calculate this, you need to check out there is 50 gram, right? And we know that ppm is about 10.10 to the power 6. You know, to convert this into grams, so you can just 50 times 0.2, and since you want to convert it in grams, you just divide it by 10 to the power 6. Eventually what you get is it is about 0.0001, so it's about 0.00001 grams. So that is the maximum permitted mass of catalyst that could be that a 50 gram of squalene might contain. Okay, now if we check out this math down here, a reactor of 200 degrees Celsius contains 8500 mole of liquid squalene and hydrogen gas at a pressure of 4 times 10 to the power 5 Pascal. Now, under these conditions, the complete hydrogenation of squalene requires 500 meter cube of hydrogen gas. Calculate the number of carbon to carbon double bonds in one molecule of squalene, and you must show your working down here. So if you do this, what happens? First of all, at first you convert the temperature, which is temperature here is equal to, you just convert it, 200 plus 273, giving you 473 Kelvin. All right, so that is basically that how you convert it in temperature, because we know that if you want to convert degree Celsius into Kelvin, you just add 273, and vice versa if you want to convert, you know, degree Celsius to Kelvin to degree Celsius. Okay, next you basically create and the subject, which is PV by RT, and then you just place the values down here. So we got 4 times, you have 10 to the power 5, and then you have V, which is obviously 500, but of course it divided by, since it's already given in meter cube, so we don't have to convert that. And then there is 8.31 times 473. So if you do this math, you eventually get about 50882, 50882.429 as the number of moles. Now you know the number of moles, all right? And the squalene moles, they have already told you the squalene moles here is 8500, right? And they told you to now calculate the number of carbon to carbon double bonds in one molecule of squalene. All right, so let us at first find the ratio of these moles. All right, so if we can find the ratio of these moles and squalene C60H32, so it is about 50882. I'm just approximately giving it 50882. So 50882 to C63, which is 8500. If you find the ratio, you get about 6 is to 1. All right, that means, what does it mean? That means for 6 is to 1 basically means that for every one squalene molecule, there are about 6 hydrogens basically. So what will be the number of carbon to carbon double bonds per molecule of squalene? So you can just multiply that uh, 6 times of it, and if you do that, so we can say that since there are 6 moles of hydrogen for per molecule of squalene, so 6 carbon di, so 6 carbon to carbon double bonds are present in one molecule of squalene. Okay, now you write the equation using molecular formula for the complete hydrogenation of squalene to squalene basically. All right, now in order to solve this, we need to check out the strat this it was right. C6, actually C30, squalene to squalane, they say. Squalene contains carbon to carbon double bond, but squalene doesn't. So obviously C30, and since it's an obviously it's an alkene, so it contains 6 carbon to carbon double bonds, so that would be 50 hydrogen, and then it's a hydrogenation, right? So you add hydrogen, and we know C60H32, We know C3862 is the molecular formula of squalene, which we found out a little while ago. Okay, moving on, the next part, they say globally 2.8 million DMK of squalene is used each year. Traditionally, squalene was obtained exclusively from shark liver oil, which is obviously a mixture of liquid. The liver of a shark yields about 300 grams of squalene. So you need to suggest the name of a suitable technique to obtain squalene from shark liver oil. Okay, so in order to solve this, there is many way. Basically, the only way you can obtain squalene from shark liver oil, basically you want to obtain squalene from a larger chain hydrocarbon chain. So the only option would be fractional distillation. By fractional distillation, you can obtain squalene from the shark liver oil. Now calculate the minimum number of sharks you can get it. Now we can see that we needed to produce 2.8 million dm cube of squalene. All right, now we can clearly see that what let us at first calculate the mass of squalene in 2.1 million dm cube. So that would be, if you just multiply 2.8 times 10 to the power 6, all right, actually 9 to be exact since it's million, times 0.86, considering obviously you got 2.8, since the density of squalene is this one, and you know the volume, so you can just find the mass. So mass by volume, so mass is volume times density, so that would be 2.408, 2.408 times 10 to the power 9 grams. So that's the mass of squalene, 2.8 million dm cube. Now if you want to calculate the number of sharks, all you do is just divide it by the mass of squalene. So we know the liver basically consists of a shark yields 300 grams. So obviously what will be the liver for each the number of sharks for this is the total number of sharks mass. Basically this is the total number of sharks mass which will be required to produce 2.8 million dm of squalene. So the minimum number of sharps would be what? You just divide it by 2.408 times 10 by 9 divided by the liver of one squalene shark, but that would be about 8.0267, 8.0267 times 10 to the power 6 gram sharks basically. So this is the minimum number of sharks required to produce 2.8 million dm of squalene. All right. Many large corporations now use squalene obtained entirely from plants. Squalene can be obtained sustainably from cornstarch with a yield of 23% by mass. The production of 1 ton of cornstarch requires 0.093 hectares of land. Calculate the area of the land required to produce 2500 tons of squalene from cornstarch, basically. At first, let's calculate the mass of the cornstarch required, which is kind of easy, right? You can just basically uh, divide 2500, and since it's 23 by mass basically, so 23 divided by 100, you can just use this and then you calculate 108. That told you what, 23% by mass, and is called for the cornstarch from the cornstarch. Is squalene is basically obtained 23% by mass from the cornstarch. All right, and we see that there are 2,500 tons of squalene from the cornstarch. So what will be the mass of cornstarch required? That's what we need to calculate that. So if you do this, we get 10869.57 tons of squalene of cornstarch required. Now the land area required is pretty simple. 1 ton of cornstarch is what? 0.093. So what will be 10,869.57? So land of corn starch required, that would be 10869.57 times 0.093. So eventually we are going to get about 1010.87 hectares. Okay, the next part of it is that we need to convert the land area from the hectares to kilometers. Well, you can just you know that 1 hectare is equal to 0.01 kilometer. So that 101 0.87, if you just multiply it with 0.01, eventually you get about 10.187 kilometer per square. That is the answer basically. All right, you can see. With this, our topic 4 is completed, and we will the rest of it will be provided as homework. Uh, we'll meet in the next session. Thank you. Bye bye.